for today. So the second speaker I'm very happy to announce is Alistair Ferguson from the University of Strathclyde. So we're very happy to have someone from Strathclyde speaking today with us. Also next week, we're going to have someone from their SPAAM chapter 2. So yeah, and Alistair is going to speak about wave propagation in randomly layered heterogeneous media. Thank you, Alistair.
Okay, you can see my screen. Okay, yeah.
Yeah, it's perfect. Yeah.
Okay. Yeah, so I'm supervised by Tony Mulholland. He's at Bristol, and Katie and Mohammed at Strathclyde. So my talk will consider ultrasonic waves and how they propagate through randomly layered materials. So these are types of materials that are like more increasingly popular in engineering applications, just because of their complex structures. So I'll show you some motivation to why we're interested in studying this. I'll take you through the kind of equations that govern the problem. I'll show you the geometry of the problem. Then we'll look at a specific example, and then some of the technicalities and kind of length scales which are important when describing these types of materials. So to begin with then, if you think of a carbon fiber material, it's constructed of these kind of fibers. So we're interested in sending a mechanical wave into these types of materials to kind of image inside and detect flaws. So in engineering, they use ultrasound to kind of determine whether there's a crack or a flaw in the material, which is obviously important because you want to change that material out. So depending on the direction at which you send a wave into this material, there's a kind of preferred directionality, and that's just due to the kind of internal microstructure inside these materials. So this is a kind of resonance frequency plot of a wave that was kind of input into this carbon fiber structure. And you can see there's this kind of preferred wave speed, and it's just due to the structure that's inside the material. And then similarly, this is a picture here. This is a kind of cross section of a weld, an austenitic weld, which is common in the aerospace industry. So when they're repairing like aircraft fuselages, for example, depending on the kind of angle the weld tool is used at, you'll get these kind of crystalline structures. So when you go to image these and kind of and check them for safety purposes, you have to be very kind of mindful that the signal that you get out is highly affected by the structure of the material. So if your kind of non-destructive testing technique in your imaging algorithm doesn't account for this, then you can get your results can be very different. And a lot of people use homogenization techniques, so they basically assume that these types of materials don't have heterogeneities inside them. So if you have a model that doesn't account for this kind of randomness, this layered structure, you'll get you won't be able to detect flaws accurately. So this is a video here of what can go wrong. So this is the this is the end of a race, and you watch this rider here. So this is a carbon fiber race bike, and you kind of see there's some kind of, if you watch here, the handlebars kind of completely shear off of the front of the bike, and this is a kind of delamination in this carbon fiber type material. So basically my project aims at studying these types of waves, and it's basically useful to have this type of model to understand and like better comment on the resolution of imaging techniques. So another important thing when considering these complicated materials is, for example, so on the left we have what's called a slowness curve. So this basically characterizes how the wave speed changes depending on the angle of the incident wave. So for aluminium, we call it, this is an isotropic material, so the crystalline structure has no directionality inside. So if you were to send a wave in, it wouldn't really matter what direction the wave would travel at the same speed. But conversely, then, if you have a material like graphite epoxy, it has this kind of bundles of fibers, so the energy of the wave will travel along these. So the slowness curve here, this basically denotes how the phase velocity of the wave will travel. So you can see it has this kind of non-linear structure. So it's very important to take account for that. And this is what my model accounts for. And then finally, this is a simulation I've created here. So this material here is a kind of layered carbon fiber structure. And this white line at the bottom is some kind of flaw we want to detect. So basically on the top here, this is a linear transducer array, and this is a sort of something you can place on top of the material you want to image. And these will kind of excite the top and send a mechanical wave in. And the idea is you want to kind of focus the energy on the area which you want to image. So for example, if you watch this video on the left, you can see that energy kind of travels along these, the energy is kind of carried away to the left. So this kind of structure is kind of dominating how the wave travels. And a cool thing you can do with these transducer arrays, you can control how they fire. So if you understand kind of how the structure of the material affects the wave, you can focus the energy. So you can set these to fire at different times, because the layered structure basically will change the speed of the wave. So you can kind of focus the energy in certain places. So these types of materials are very tricky to kind of get information from the signal, the output signal, when you send a wave in. So I'll start then the kind of maths, the model behind how to understand this. So we model horizontally polarized shear waves. So we have the elastic wave equation, and we have this displacement vector, Hooke's law, and then basically we have the stress strain tensor. So this is a deterministic model of how a wave would travel in such a layered material. And then we have this kind of angle theta, which we use to control the kind of slowness surface. So how this layered structure influences the wave. So the material kind of, when you send the wave in, it will vibrate in certain planes, and we assume that we have this kind of in layer vibration for this kind of carbon fiber structure. So when we send in a nice monochromatic wave, we have this layered structure we assume to exist inside the material, and in each layered structure, basically these arrows denote the kind of orientation of the fibers inside each layer. So we assume these to be kind of randomly varying as the wave propagates through the material. So the kind of, you send a very nice wave in, and because the material is interacting and causing scattering in each layer, the output signal is this kind of incoherent mess. And being able to understand this output signal is kind of key to imaging in these materials, and kind of commenting on flaws, or trying to send the energy to a certain place. So this is how we introduce the randomness to the model. So we assume this kind of grain angle, or the fiber angle, has this random nature. So this M here will be our kind of Markov process we'll introduce to the equations. So now I'll show you a kind of further into the problem. This is called the kind of weakly heterogeneous regime. So it's a common regime found in the kind of engineering industry. So imagine you have this material of length L, and it's comprised of layers. In practice, this is a kind of blown up picture. But you kind of assume the wavelength of the input wave is kind of commensurate with the size of each individual layer. So this will basically mean that when the wave enters, you have this scattering effect, because the wave is kind of interacting at a kind of very small distance. and what the wave you get out will be highly attenuated, etc. So we assume we have a high frequency wave, and then we have this fluctuation, which we call sigma. So it basically allows us to kind of tweak how random the material is so that we can control it. And then this is just, yeah, so the propagation distance is much larger than the wavelength. So we not dimensionalize the problem, very standard, the distance, frequency, and wave number of the input wave, and then we have some non-dimensional parameters in the problem which help us kind of scale things, and that will be kind of important later. So we can do more work with the model, and we derive this kind of standard stress strain evolution equation. The important thing to note is now, if this was a homogenization model, so you don't account for any kind of fluctuations in the material properties, this M, which is our Markov process, this would essentially be zero. So if we were to set zero in this case, we would kind of recover a deterministic problem. But we keep this M in as a kind of important thing, and it's what differentiates our model from the kind of simplified deterministic models that a lot of people use in their imaging algorithms, etc. So we've non-dimensionalized the problem here, and the other important thing is we've defined this parameter. It's called this parameter nu, which kind of couples the non-dimensional wave number and the angular frequency. And it turns out this nu is actually a steering parameter, so it's a kind of quotient of wave numbers. So if you remember at the start of my talk, I was kind of talking about arrays. In arrays, it's very common that you kind of want to steer the wave in a certain direction which you input into the material. So we kind of have introduced this, which is nice, into the model. So we can actually study how the kind of directionality of the wave influences things like the coherent part of the amplitude. So how the material causes the wave to kind of decay. So it's important, and it's kind of a new thing. So I have had to skip a lot of details, but basically from the stress evolution equation and the velocity evolution equation, we can do more work to find the wave mode amplitudes of the system. So we have this random matrix equation that looks like this, and we have this 1/epsilon scaling out front. And this actually falls into a certain class of equations we can use a limit theorem on. So this H matrix here basically captures the material properties. And then out front we have a random process M. And the important thing to note about this H matrix, which is really nice for solving this thing, is it has trace zero. So you can use, it's called Jacobi's formula, which basically says if the trace is zero, you'll have like some kind of conjugate symmetry in the system. So this kind of random equation here is coupled with this wave mode equation. So this P matrix is very important. It's called the propagator matrix. So this basically, in the problem, it physically like propagates the wave from this. So when you send the wave in, you think of that as the first interface. So this P kind of propagates the wave through the material, through the layers, and this is what we'll use to kind of quantify the decay of the energy, etc. So chi and var kappa, I'm sorry, they look very similar. I didn't have time to change that. But it has this kind of complex conjugate symmetry, which is very nice for solving this problem. And the determinant of P has this, it's kind of a conservation of energy relationship, and that comes from as well the fact that the trace of this is zero, and using Jacobi's formula. So once we have that equation, then for the propagator matrix, use the diffusion approximation theorem to solve this thing, and we basically end up with this Strathclyde SDE. So we want to kind of solve for this P here, and we'll basically be able to access the statistics of the propagator matrix. So this will give us access to the reflected, transmitted energy, etc. So because it has this nice conjugate symmetry, it actually decouples. So this is this matrix equation here decouples into two SDEs, and these A1, 2, 3 constants basically contain information about the material. So you can plug in stress values and kind of study a real material, and I'll show you that at the end. And the other important thing is these epsilons. These are the correlation integrals. So you can, I haven't had time to show it here, but we've numerically simulated these, and you can, these as well contain information about the kind of grain structure inside the material and how coarse it is. So that's important as well, but these things are positive. So I'll just jump in then to how we solve this thing. Because we have that nice conjugate symmetry, there's a parameterization you can use with hyperbolic functions, like so. And we just want to look at basically the real part, the kind of amplitude of the wave. So we can simplify the problem, use the chain rule and the Strathclyde regime to convert into these gamma, phi, and psi variables. We can reduce it and write it in Ito form. And we do this because we want to basically compute the generator of this process here to obtain the statistics of it. So the generator for this system turns out to be this. And that's the kind of a good point to kind of now we have all the information we need basically to find the statistics of these things. So if you think back to the beginning, this example where we have this input wave, so imagine it comes from some kind of array, you'll get some reflected part and transmitted part, and we want to find out how this material has affected this transmitted part here. So if you have this matrix equation, you can basically write down boundary conditions for this problem, and you can do some algebra and you get expressions for the reflection and transmission coefficients. And we've solved the SDEs to be able to find what the var cap and var chi things are. And remember, we parameterized them like so. And then we just want to look at the amplitude part. So we define something called the power transmission coefficient. It's this absolute value squared. And this basically characterizes the amount of energy that moves to the right in the slab. So it's like the transmitted energy. If we send in, say, a unit pulse of 1, how does that decay according to the material properties? And because we have the generator of the gamma process, we can basically rewrite it in terms of this eta. It just simplifies things. So we can find what this operator is. It turns out to be self-adjoint. And we have this parameter out front, which is 1 over L log. So we call this the localization length. And I'll show you what this is in a second. But this basically characterizes the decay of the amplitude of the coherent part of the transmitted wave. So once you have this generator, you can form what's called the Fokker-Planck equation. So this P is the probability density function of this eta process. And basically, we want to solve this PDE to find that P, and then we can compute the moments of this tau. So it will give us the statistics of the transmitted energy. And the right-hand side of this actually decouples, sorry, it doesn't decouple, it reduces very nicely to this kind of Legendre type differential equation, and we can solve this quite easily. So the localization length, which appears in front of this generator in this PDE here, I'll show you kind of what that is. So if you remember back to the Ito system we had before, if you take one of the equations here and integrate it across the whole of the material, so the whole random material, and then you take exponents, basically we're aiming to kind of write this in terms of this hyperbolic function here. So you can basically reduce this and equate it to the power transmission coefficient. And it has this, it basically is dominated by this exponent term here. Everything's been non-dimensionalized. And this L log is a kind of decay coefficient of the power transmission coefficient. So this kind of so this term here encapsulates all the material, all the information about the material, and how that affects how the energies kind of decays as you send in the pulse. So this L log contains a bunch of things, but one of the most interesting things of kind of how to analyze it and see how it changes is to investigate how it changes with this new parameter, so the kind of steering of the wave, and it kind of has this nice decay as you increase nu. So this kind of corresponds to a greater angle of incidence of the wave. So it's not the full picture, but you can think of it like as nu increases, the angle of incidence increases. So as the wave kind of travels through each layer, it will scatter more, and it will have a larger propagation distance. So with that being said, then we can, if I return back to basically solving this equation, the right-hand side, we can solve this by using contour integrals, etc. And then we use the Meller-Fock transform when you have these hyperbolic functions. And it turns out you can write this nice analytical expression for the probability density function. And then once we have this, you can basically compute moments of this tau, this power transmission coefficient, which is what we want. And notice you have this L log term appearing. So this is a kind of the decay part, and we know what that is from the phi SDE. So we have some nice results of how the mean of tau kind of changes with this parameter nu. I mean, you can plot it. I've just chosen this as like one example, but there's a lot of things you can plot because L log is like a complicated parameter. And then the standard deviation, you can kind of see the peak shifts. And yeah, there's a whole host of reasons why this happens, but I don't have time. So yeah, thank you for listening. So just to recap, yeah, we've kind of derived a model for wave propagation where you can't assume the material is homogeneous. We have this kind of beam steering parameter, which is important when you're modeling arrays and such. You have this directionality, and then we have solved these SDE systems and commented on the statistics of things. And it's kind of important. What I'm working on now is using this model to comment on things like the resolution limits and imaging techniques. So with this forward model, we can use it in a inverse problem to do nice things like time reversal. So you can flip the wave, send it back in, and you can focus the beam on certain things. And yeah, it's very interesting. So hopefully I've convinced you that it's an interesting problem to study, and it kind of touches on a lot of areas of maths. So thanks. Thank you for listening.
Right, so before I stop the recording, let's just get a round of applause on camera for Alistair. Okay, and I'll stop the recording now and ask people if